All right, so we're going to start today by taking a look at Morse code. Some of
7 days
you,
left.
7 days left. Wow. Peter was right on top of that. He knows his Morse code.
I
He was
don't.
able to decode that, and he found out that after today there are 7 days left. Okay, so Morse code has been around historically quite a bit, and we start to wonder, where did it come from? How was it created? It was a nice way to send messages, but when I look at this and I see 7 days left, S is dot dot dot. We also know O, dash dash dash, right, for SOS, but E is just a single dot. Here's a V, dot 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 dash, quite a bit longer. Here's an E. This is an N. And if you play Wheel of Fortune, you know that there are some letters that are more common than the other. So why is E a dot and why is V this long mess?
E's a vowel.
Yeah, E's a vowel, and it's also probably more
Common than V.
common, right? It's more frequently used. So, there's rhyme and reason of how this was actually developed. And the way it was developed had something to do with an actual binary tree. And if I can share my screen, let's come over to here and get out of there. Go on, I can't get rid of that top screen. Here we go. So I'm going to come in here and I'm going to say Morse code, and let's see what we come up with. And I think I've already showed this to you once. And if I have an image, and I may have to type in binary tree, and all of a sudden I'm going, whoa, there it is. I have one. E is a bunch of dots. T is a bunch of dashes. Okay, E and T are actually pretty popular letters, aren't they? I, A, N, and M. So this binary tree, where every parent has two children, nothing up at the top, just a root, it keeps going right along with what we've been talking about. So everything was put in a certain spot for a reason. Why this between L, P, and J is a blank and then it goes down to a plus, I don't get. But, there could be some significance to if all the letters are, within a 1, 2, 3, 4 dot or dash range kind of deal. So there was thought put behind this. Now, when we looked at this, it was decodable, right? We can decode this. We can immediately encode a message if we wanted to. I took the message I wanted. I looked at the chart, and this is what I came up with. Now, we need to be a little more efficient. We want to be able to send messages the same kind of way, but with less going on. And some of what I mean by less going on is, what if I could get rid of the spaces? Might make it a little hard to decode, but we're going to look at a way to do that. Okay, so we just talked a moment ago about shorter code for letters that occur more frequently, like E. Okay, spaces are a problem. And then, is it decodable? Yes. If I didn't have spaces, is it decodable? No. And we just looked at why is E less than Z, and we could make up our own. We could go back in 161 where you did sonnet 18 and you got the frequency of all of the letters. You took that sonnet, you opened it up, you counted the A's, you counted the B's, you counted the C's, you counted the D's, and so on and so on. Well, the way this is done to build our own secret code, we're going to start by finding the frequency for each letter, and that frequency is going to determine our what we call weight. Okay, so how do we do this? Well, we're going to use something called a Huffman code, and as you can see, it's going to use a data tree, and it's going to be built for what we call data compression. We've started talking already about this variable length code, shorter code for codes that occur more frequently, okay? And we want to get a character weight. So say I came up with a new language, and in my new language, the only letters I had were A, B, C, D, E, and F. And I went through and counted them all up. And as I counted them up, I found out that, yeah, once again, in my new secret language, E is the most popular. And what percent of the time does E come up? Play along. What do we got? E's real popular.
35%.
Okay, so there's 8 of them on a, so E comes up 35% of the time. So we're going to give it a weight of 0.35 because we want to make this the most efficient we can. What's the next popular letter in our secret language?
A.
A. That comes up how many, what percent of the time?
30.
30. Okay, we have to be careful. We're up to 65% and we still have 4 left. What's the next popular letter?
B.
D, 20%. That gets me up to 85. And I'm thinking that the rest of these are probably going to come up close to 5%. Okay, so my weights, my frequency weights come out to be a total of 1. So if I looked at 100 characters, only 5 of them are F's, 5 of them are C's, 5 of them are B's. Okay, so now what are we going to do? Well, we're going to take this and we're going to build ourselves a binary tree according to these weights. Now we're going to look at individual weights, and then as we go, we're going to look at combination weights. So when I mean look at individual weights, what are the smallest 2 individual weights? Well, I have 3 of them, so I can pick any 2. Which 2 would you like to pick? Pick B. Pick B. B. All right, good. B. So I'm going to pick B, and I know that the B is it's a 0.5, right? A point. Hold on, nobody caught this. 0.05, 0.05, 0.05. I was waiting to see if anybody caught that. 0.05, and I'm going to pick, let's just go with C, 0.05, and I'm going to combine these to get a 0.1. Now, B and C are off the table, but BC is now on the table. What are my next 2 smallest frequencies? Because there are what's going to be combined. Well, let's see. I have a 0.05 and a 0.1. So I'm going to have to go with F. This gives me a 0.15. F is off the table. What are my next 2 smallest frequencies? This combination and D. Huh. That's going to give me a 0.35. Okay, so D is off the table. Now I have a 0.30, 0.35, and a 0.35. So it looks like I'm going to combine A with either E or with this group over here. What would we like to combine A with? E. Okay, good. A, 0.30. E, 0.35. And these 2 are going to combine to give me a 0.65. Now, A and E are off the table. These 2 combine to give me 1. I love it. I love it. We're almost there. Second half of the class is wacko, but we're almost here for this first. All right. So now I'm going to get ready and I'm going to fill in 0s and 1s. 0 to the left, 1 to the right. 0 to the left, 0 to the left, 0 to the left. 1 to the right, 1 to the right, 1 to the right, 0 and 1. Nice. So now I'm going to take a look at my letter A. A, what's it go with? If I start here, it looks like A is what?
0.
1, 0. Okay, if I follow down the path like I did with Morse code, A is going to be 1, 0. B is going to be 1, 2, 3, 4. Yeah, so B is less frequent. It should have more numbers. C. 0, 0, 0, 1. D, D's over here, 0, 1. Nice. E, E's over here, 1, 1. F, 0, 0, 1. Okay, now, by the way those numbers have all worked out, I should be able to create a Huffman code, which is right here, a message using that Huffman code that is immediately decodable by you. Here we go. Decode that. It's top secrets. It's all zeros and ones. No spaces. What's the first letter have to be?
F.
F. Yep. F.
I'm gonna give it a guess. It's gonna be like Faded Glory or something.
Well, there's no L or G.
Okay, well I just got like faded now. I was like,
All right.
maybe.
F, A, D, E,
Okay.
D.
Yeah.
Finish it up.
AFE.
What's the end of it?
Is it AFE?
ACE.
Yeah, I'd say like ace.
Yeah, you're right.
Faded ace.
So it ends up being something called faded ace. Now, I'm going to take a look at this.
You'll need to unlock your iPhone first.
I'll be quiet. If I came back up here with my Morse code and I counted the number of characters, how many characters are there? And you would have actually count the spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Even the space from here to the next line. Count them all up. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 30, 31, 32, 33, 34, 35, 36, 37, 38, 41, 42, 43, 44, 45, 46 characters. Okay, I made a note, 46 characters. This was, my message was 7 days left. SEVENDAYSLEFT. That's 13. 13 letters. So if I do a quick division, this is what's 46 divided by 13? 3 points. About 3.5. Hey Siri, what's 46 divided by 13?
46 divided by 13 is about 3.5384.
Okay, so that means for every letter I wanted to use up here in Morse code, if I count the number of characters, dots and dashes, same as ones and zeros, divided by the number of letters, my average character length is 3.5. Well, if I do the same, oh, waka, waka, waka. If I do the same thing here, let's see, how many characters do I have? 2, 4, 6, 10, 12, 14, 16, 18 divided by 2, 4, 6, 8. My average character length is 2.25. Which one do you think is better? 2.25, 3.53. So we were able to come out and create something that is immediately decodable, way more secretive. I mean, if you don't have this, you're not getting this. Unless you have a program that can run through and do, you know, whatever number of permutations and combinations and salutations, whatever it takes to break that code. A Huffman code, top secret stuff. Another example here, we start talking about what we have going on here. And, you know, if I count, look at the weights, I look at how many characters there are on each piece of Morse code. I see the expected character length is 2.1. Now, if we did a message like faded ace, we could see an actual character length. But here we have something called an expected character length. If I came back over here, what would my expected character length be? Well, let's see. I have an A 2 times 0.3 plus a B 4 times 0.05 plus a C 4 times 0.05, D 2 times 0.2, E 2 times 0.35, and F 3 times 0.05. Oh, I'm sorry, I was looking at my paper on it. 0.6 plus 0.2 plus 0.2 plus 0.4 plus 0.7 plus 0.15. Oh, geez. 6, 8, 10, 14, 21, 22 and a half, or 2.25. Is that what it comes out to be? 2. Oh, look at this. We accidentally kind of almost got what it should be. Now, not all of them are going to be this. We just accidentally got it to work out perfect. So in ours, the expected character length is a little bit lower, where it should be 2.25. We actually did an example and it came out to be exactly 2.25. But our goal is to get the smallest expected character length as possible. And the way we do it is with a Huffman code. Questions? Questions? We're good, we're happy. Do we need to do another one? Are we good? All right, I'm going to move on. All right. The next section, section 15.2. So sometimes when I build a tree, my tree could get really ugly. And for example, if I said I want to build a tree with the numbers 2, 4, 6, 8, 10, and 12. So if I build a binary tree with these numbers and I wanted to search, my worst case scenario is big O sub n. It's not ideal, is it? Because I'd build a tree and I'd say 2. My next number is 4, goes to the right. My next number is 6, it goes to the right. And you see what kind of damage keeps going here. My search would be dot, 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 all the way to the end. Okay. But these two guys, Adelson and Adelson Velsky Landis, okay, these two guys got together and said, well, wait a minute. If I look at that tree, 2, 4, 6, I know another tree that I could have that could be a substitute for that, that would be more efficient to search. And I'd have to make a slight change. Give me another tree, another binary tree that looks like this. Well, not like this, but has these numbers in. That would be much easier. Instead of taking this many steps, could be done in smaller steps to do a search. What would it look like? What would the root be? Well, we don't want 2 as a root. That's no good. What would we like to be our root?
4.
4, thank you. So if I had this, no, I don't really like that so much. Kinda. Wait a minute. I do like this. If I look at the parent, a number smaller is to the left, a number bigger is to the right. My search would be of length 2 instead of the length 3. So Adelson-Velsky said, well, if I get this kind of look, I'm going to want to do some kind of rotation. Now, how did they know this kind of look came up? Well, they went back to what we called the balance factor about a week and a half or so ago. And if I looked at the balance factor, I remember that's something, okay, if I want a balance tree, what were the 3 numbers I needed for balance factors? Well, I have them written down, so it shouldn't be too bad. -1, 0, and 1. And if I took a look at this tree, it's not very balanced. Its left subtree, 0, minus its right subtree, made this a -2. It made this a -1, and this is 0. So I don't have that ideal balanced factor to have a balanced tree. Because if I had a balanced tree, it would be much easier to search. So they came up with this idea of being able to rotate to give me a better looking tree. Now, am I thinking world class here? How would I code this? Oh, I'd have to be able to calculate the balance factor. And depending on what it is, I'd have to have a certain kind of rotation. What if I had this tree? 6, 4, 2. Looks like I'd need to do some sort of right rotation to give me 4, 2, 6. I still have a binary tree. Numbers to the left are smaller, numbers to the right are bigger. But I'd have to do some sort of right rotation because now I have a balance factor of 2. This is 1, this is 0. If I look over here, I have a balance tree. So there's 2 of the types of rotations that Adelson-Velsky performed. A left rotation, a right rotation. Now, there's going to be 2 more rotations that are going to go on. And we're going to take a look at an example and see how far along we can go. All right. So my example is I want to put in the states, Rhode Island, PA, Delaware, Georgia, Ohio, Massachusetts, da, 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 da. I want to put them in alphabetically. So that means alphabetically less than goes to the left, alphabetically greater than goes to the right. So let's see what we have. We talked about maintaining our balance factor. Okay. Rhode Island red, you're good. What's its balance factor? 0. Okay. PA, A, B, C, D, E, F, G, H, I, J, L, M, N, P. P goes to the left. Balance factor. Looks good. Okay. Delaware. Uh-oh. Delaware is going to go to the left of PA. Now I have Rhode Island with that bad balance factor. I want to balance this tree. I'm going to do a right rotation. I'm going to make this PA. I'm going to make this Delaware. I'm going to make this Rhode Island. Coding wise, I would say if this is the, then I need to make this the, but its right child now gets the value of Rhode Island. The root now points to PA. And, you know, this is one of those where you'd have to sit and look at a lot of patterns and draw the picture, draw the picture, draw the picture until something starts to come out in the wash. All of my balance factors are good. Okay, again, this became a +2, so I knew I had to do a rotation. Let's see. I need to keep track up here. All right, next one I'm going to add is Georgia. Georgia goes where?
To the right of Delaware.
Thank you. To the right of Delaware. Check all my balance factors. Am I happy? Yes. So again, we're just playing with binary trees every day. Ohio, where does it go?
To the right of Georgia.
To the right of Georgia. Okay. Now we have problems. PA is now, oh boy, that's a 2. Delaware is a -2. This is a -1, a 0, and this is a 0. So now, what do you think we're going to rotate on? There's only 5 to pick from.
Delaware.
One suggestion is Delaware. What do you mean by picking Delaware, Peter? What would you say is going to happen? Going to rotate it this way? How about more of a rotation on Georgia?
Georgia, yeah.
And, you know, one of the patterns that slowly gets picked up is how I have to rotate down below. So if I rotate it on Georgia, I have PA. I come over and have Georgia. Now, when we do the left rotation, Delaware comes down here. Ohio stays as the right child of Georgia. Rhode Island didn't have to move. If I check all my balance factors, am I happy?
Yeah.
Yeah. Next one I'm going to add, Massachusetts. Where does Massachusetts have to go?
To the left of Ohio.
To the left of Ohio. And when I put it in there, oh, oi polloi, this is now +2. Rhode Island's a 0. This is a -1, right? This is a -1, 0, and 0. I have a problem because one of my balance factors is 2. Oh boy. Now, this is where it starts to get crazy. And I'm glad I don't have to ever code this. But conceptually, hopefully you understand that the benefit of Adolph-Belsky making a tree balanced avoids one of those really lopsided trees. So here's what's going to happen on this one. We're going to do a left rotation on Ohio to solve this. We're going to do a left on Ohio and a right on Georgia. I need to make sure I have this straight in my head. Okay, so if I do a left rotation on Ohio, I better do this in pencil just in case. A left rotation on Ohio. Okay, so now Ohio is here. What would be, I just got a brain fart. We go a left on Ohio and then a right on Georgia. So on Ohio, I have Delaware's to the left. I'm messing this up because Massachusetts would have to go here. Then I have Georgia. Then I have PA. Then I have Rhode Island. And now I do a right on Georgia. So that I have Georgia up here. I have Ohio here. I have Delaware. That's not a D. Massachusetts. Over here, I have PA. And I have Rhode Island. Woo. So I did the left on Ohio that moved him up, even though it looks really odd right now. Then I do a right on Georgia. When I do the right on Georgia, PA is still greater, Rhode Island is still greater. 1, 2, 3 minus 2, a balance factor of 1. Ohio has a balance factor of 2, doesn't it? So I messed something up.
Why did the Massachusetts get attached to Delaware in that rotation, the first one with Ohio?
Well, when Ohio rotates up, Massachusetts has to stay. So the left bunch of the guy getting rotated up attaches to the right of the left child. But I thought I did it right, but Ohio has a balance factor that's off. So I did something wrong. But yeah, that's a good question, Matthew. And I think we've seen that before. When I move up, this detaches and goes to the right. All right, let's go to my notes. Compare what we did. We had let me come back up here. When I do this, Ohio goes up. Ah, my mistake. I see what I did wrong. Yeah, now you know why I'm not a big fan of Adolph-Belsky and how they came up with all this, because they probably drove themselves crazy. Let's come back up to here. When I rotate Ohio up, Georgia doesn't hang out up there. Georgia gets changed. Georgia gets moved down. Ohio's the one that all the action happens on. Calc proof on the board. Oh, erase the first 2 boards. Let's see what we have. Ohio rotates up. So when Ohio rotated up, Georgia and Delaware stayed here. Massachusetts attaches to where?
The left of, the right of Georgia.
to the left, to the right of the left of, yeah, it attaches here. So Massachusetts went here. Here's PA. Here's Rhode Island. So I rotated on Ohio. So Ohio went up and everything else came down except Ohio's left attached to the right of Ohio's new left. And now I do that right rotation. Now I bring Ohio up. Oh, please work. PA goes here. Rhode Island goes here. To the left of Ohio is a Georgia here, a Delaware here, and a Massachusetts there. Yay! I do a left rotation on Ohio, then a right rotation on Ohio. Balance factors are all good. I now add Illinois. Where would Illinois go?
To the left of Mass.
Yeah, right there. Okay. My next one is MI, Michigan.
To the right of Massachusetts.
Yeah. So I don't have to do many of these left, right, or left, right rotations. Because here I did a right, here I did a left. When I got trouble here, I did a left, right. Okay. But now I'm starting to get more room and more room that, you know, oh boy. After Michigan is Indiana. To the right of Illinois, I start looking at my balance factors. I have a -2. Yuck. What is this one? 1 minus 3. I have a -2 there as well. You know, one of the things is I had a +2 and I did a right rotation. Here I had a +2 and -2. I did a left and I solved it. Here I had a +2 and I had to do a left right. So there's other factors that are going to come into play. How do I know what node to rotate on and what kind of rotations to do? We don't have the time in the course to go into that depth. We need to continue with the breadth of the course. But, you know, this is, wait, that's a +2. What are we talking about? This is a +1. Here's a 0. Here's a -1, 0, 0, -1, 0. So now I'm going to have to do some kind of rotation. And a part of me wonders what I would rotate it on. Does anybody know?
Probably Georgia.
Probably Georgia. Possibly. I'm thinking maybe Massachusetts to do a left, you know, and Michigan's still there, but then Illinois would attach to Georgia and then do a right, and then Michigan would have to be to the left of Massachusetts. Shall we try it? Say yes.
Yeah.
Okay, so I'm going to do Massachusetts. When I rotate that up, I have Georgia. I have Delaware. Okay, I said the left is going to attach to the right. So Illinois and Indiana are going to go here and here. Okay, I still have Michigan over here. It goes up to Ohio, down to PA, down to Rhode Island. Now, when I rotate this up, Massachusetts right is going to attach where when I rotate down? The upper one's left. Just like when I did this, Massachusetts left attached to Georgia's right. When I go up, Massachusetts right is going to attach to Ohio's left. So now Massachusetts is up here. We know that PA is going, excuse me, Ohio got moved down. PA is still here. Rhode Island is still here. MA's right is going to attach to Ohio's left. And then what do I have left here? I have Georgia. I have Delaware. I have Illinois. And I have Indiana. Yay, I got that one right. Every parent is greater than its left, less than its right. Balance factors across the board look pretty good. So when I got in trouble here, I did a left on Massachusetts, then I did a right. So I did a left here, and I did a right here. What do you think about that? Checking my notes. We got that, we got that. That was just another old example. Scribbling all over the place. Shall we partake in another example of AVL? I can tell you want to. Another example of AVL. I got stuff all over the place, folks. Somebody say yes.
Yeah.
All right. 14, 16, 4, 6, 8, 10, 9, 5, 1. I don't know. I just made some numbers up. Go ahead. Build a binary search tree using Adelson-Velsky-Landis to keep it balanced. All right. I don't know. Is this easier? Whoop, whoop. I got the first 3. I put the 10 on, it looked like I had to do a left, right. I put the 9 on him. I still balanced.
Yes.
Yeah, I'm still good. 5. 1. Hey, did it.
So
Is that
five should be the right of 4, right?
Say again?
5 should be the right of 4.
Yeah. Darn it, I thought I did it perfect. Thank you. That'd be a good test question, wouldn't it? Has a couple rotations in. Questions?
Is there a problem with the 6 now that that's not balanced?
Yep. What do you do, Matthew? 6 is not balanced.
So I think it was when you add the 5 in before you add in the 1, we probably needed to do something at that point.
Yeah. So up here, I did the right rotation. Thank you. I got the 8. I had 14. 10 attached to the left of the 14. I have the 16. Coming over here, I have a 6 and I have a 4. All right, so that was after I added the 10. I now add a 9. Where does the 9 go?
To the right of 6.
No, it's bigger than 8.
Oh,
So I
to
start
the-
here, go
to the
bigger than
left of
8,
10 then.
go to the left of 10. 5. To the right of 4. 1. Okay, we're still balanced. Good catch, Matthew. Now I can put that example on the test. Those numbers I just made up.